So I tend to tweet a lot. You can follow me if you want. And I'm running the Porto chapter of Papers We Love. If you don't know what Papers We Love is a repository of academic computer science papers and gathers a community who loves reading papers. So there's lots of chapters in the world, and I'm running the Porto chapter for more than a year, and it's been a great experience. And I tried to merge the meetups with companies, and we started a reading group session at my company. We pick up a paper every 2 weeks and read them, and eventually at the end of the 2 weeks we share our experiences. And this process led me to this paper written by Rolf Merkle, which is a digital signature based on a conventional encryption function. Um, it was written in '87, and Rolf Merkle talks about a new digital signature that is able to sign an unlimited number of messages. So this new system is able to sign this unlimited number of messages, and the signature size increases logarithmically as a function of the number of messages signed. So basically, the main goal, the general idea, is to use an infinite tree of one-time signatures. If you try to search Merkle trees right now, it will eventually point out to this paper, because there's lots of blog posts on cryptocurrencies that will point out to this paper as the original paper of Merkle trees. But that's wrong. Merkle trees were invented in '79, also by Ralph Merkle, and they were introduced in this thesis: secrecy, authentication, and public key systems. He talked about lots of things. He talked about one-way hash functions, public key persistent, public key distribution, trapdoor knapsack, and eventually he talked about a new certified digital signature, which describes the Merkle trees. So eventually, this chapter in this section from the thesis eventually was published 10 years later as a single paper, a certified digital signature. And if you follow that link over there, Ralph Merkle explains why this paper took so long to be published. But a Merkle tree is also known as a binary hash tree. So basically, it is a data structure for efficiently summarize and verify the integrity of large sets of data. And this will enable users to verify the authenticity of the received responses. And initially, it was used for the purpose of one-time signatures and the in authenticated public key distribution. Namely, you will be able to provide authenticated responses as to the validity of a given certificate. So this is what a Merkle tree looks like. It looks like a balanced binary tree, but it contains at the bottom the data blocks. It contains leaves that are hashes of data blocks, and we'll use recursion to compute the Merkle root. So the Merkle root is a crucial piece of data because it allows computers to verify with incredible speed and efficiency the information if a given information is present in the tree. So at this point, we are able to identify the two main purposes of Merkle trees. The first one is to summarize large sets of data, and the second one is to verify that a specific piece of data belongs to a larger data set. So before diving into Merkle trees and one-time signatures, let's first talk a little bit about one-way hash functions and why they are super important in Merkle trees. So a one-way function, f, is a function that is easy to compute but very difficult to invert. So the idea is to take large inputs and return a unique output with a fixed length size. So as you can see in the middle, it is the function. It should be pure because you take an input and it should return always the same output. And given the input and the function, it's easy to compute the output. But given the output and the function, it is effectively impossible to compute the input. So that's why they are especially useful in Merkle trees, because mainly for two obvious reasons. The first one is storage, and the second one is privacy. So take, for example, systems that contain massive amounts of data. The benefits of being able to store and identify data with a fixed length output can create vast storage savings that will help you to increase efficiency. And related to privacy, we know that the person who computes Y is the only person who knows X. And if Y is publicly revealed, only the originator of Y knows X and can choose to reveal or conceal X at his whim. So they are also important in one-time signatures. They were introduced by Leslie Lampert in '79. And most signature schemes rely in part on one-way functions, especially and typically hash functions, and they rely on them for their security proofs. So the beauty of the Lampert scheme was that the signature was only relying on the security of these one-way functions. Although these one-time signatures were very practical between a single pair of users who were willing to exchange a large amount of data that was necessary, but they are quite not practical for most applications without further refinements. Take, for example, if 1,000 messages are to be signed before a new public authentication data is needed, over 20 million bits or 2.5 megabytes must be stored as public information. Even if this is not overly burdensome when we are having only two users, A and B, involved in this kind of signature system, if B, the user B, had to keep these 2.5 megabytes of data for another 1,000 users, it would mean that B, the user B, will have to store 2.5 gigabytes of data as public information. And if you increase further the number of users or the number of messages to be signed, the system will eventually become burdensome. So Merkle at this time focused on improving the one-time signatures and how to eliminate the huge storage requirements in this Lampert scheme, and proposed an improved one-time signature that reduces the size of the signed messages by almost a factor of 2. And this new method was called tree authentication, because the computation of the root hash forms a binary tree of recursive calls. And by using this method, we can have less and less transmissions required. And if you look closer into the algorithm, it will reveal that half of the transmissions are redundant. So let's see how we can compute a Merkle root, given we have a file and it's separated as data blocks. So let's assume that we have two data blocks, L1 and L2. The first step is to apply the one-way hash function to L1, and that will output a given checksum, 9EC4. The second step is to apply the same one-way hash function to L2, and that will output another checksum, 7E64. So in order to compute the parent node, we'll have to concatenate both child hashes. So every time that we want to calculate this parent node, we need to take the hash of L1, concatenate with the hash of L2, and apply the same one-way hash function once again. So this will eventually output this checksum, and we have a Merkle tree completed. So at this point, we know the building blocks of a Merkle tree. Let's try to represent it with Elixir, and let's start by defining a leaf. So as you can see, a leaf should contain an hash, and it's pointing to a data block. So we need to store that value. So we can do that by creating a new module, Merkle Tree .leaf, and define a struct with two properties, hash and value. In this case, both hash and value are strings. The next type to define is node. As you can see, a node should contain an hash and the left child and the right child. So we can define it as well by creating a new module, a Merkle Tree.node, and define a struct with three properties, hash, left, and right. Once again, the hash is a string, and the left and right can be either a node or a leaf, depending on the depth of our tree. So the last node represents the Merkle tree as a whole. So it is the Merkle tree root, and we can define a Merkle tree module with a struct with a single property root, which is nothing more than a Merkle tree.node. So we know the basic blocks of Merkle trees so far. So the next step is to take the data blocks and hashing, apply the one-way hash function and convert them into proper leaves. So by that we need to define a new module that is able to apply the hash function to our input, and we need to create a new function in the Merkle tree module that accepts a list of blocks, apply the crypto hash function to each block, and builds a proper leaf. And this build function in leaf is nothing more than an auxiliary function that takes a value and the hash and returns a proper leaf. So if you call the new function in the module Merkle tree with this input, so we are passing two data blocks, the output should be something like this. We are converting the data blocks into leaves that contain the data block value and the corresponding hash. We are doing this for L1 and L2 as well. So the next step is to take this pair of leaves or nodes and hash them once again in order to compute a new node. So we need to create a new function within the nodes module that in this case will accept a pair of leaves or nodes, and we'll take the hash of each node, we'll join them together and map it in the same pass. So we are moving from a pair of nodes to a single string that represents the concatenated hash, and we apply the same one-way hash function once again, and we call the build function that is responsible for taking the new hash and the original childs, and we are pattern matching here the left and the right, and we are returning the node struct with the three properties populated. So if you take a look back at our currently output, we have a pair of leaves. If we call this new function in node and passing the pair of leaves, the result will be something like this. It will be another node, a new node with a new hash that contains a left leaf and a right leaf. So you may be wondering, you talked about recursion, but we are not using recursion. We are not using recursion because we are just passing two data blocks, and we are able to to compute the Merkle root with just one pass. So if we are passing a bigger file, so we have 4 data blocks, L1, L2, L3, and L4, we are able to use recursion in order to compute the Merkle root. So the first thing that we need to do is to convert the data blocks into leaves. We know already how to do this. The second step is to take the pairs of leaves and convert them into a new node. We know already how to do this as well. So at this point is where the recursion needs to kick in. So we have 2 new nodes, and the next step is to take that pair of nodes and compute the Merkle root. So having this way of build a node from a pair of nodes or leaves, we can now make use of recursion to calculate the nodes up to the Merkle root. So if you recall this function, it's currently yielding a list of leaves. We need to define a new function that will accept that same list of nodes, and with the goal of grouping that list of nodes into several pairs of nodes in order to build another node by concatenating both the left and child hashes. So for that, I'm building a new function called build that accepts a list of nodes, and it's responsible for chunk this list of nodes every 2 elements. So if you are passing this list of nodes, this list of four nodes, we apply the chunk every 2, and it will output something like this. So at this point, we go from a list of strings to a list of pairs of strings. That's precisely what we want. We want to take each pair of these and apply and call the new function in nodes. So we are moving from a list of nodes to a list of pairs of nodes, and with each pair of nodes we are able to compute a new node. And we call the build function to continue the processing. Notice that we are making use of tail recursion in order to compute the Merkle tree, to build the Merkle tree up to from the ground up to the root. But still, we need to stop this recursive processing, right? That's why we need another signature, the same function build, but this time we are pattern matching a single element. Remember that we are in the previous slides we are moving from leaves to nodes, and we reach when we reach the top we have only 2 nodes, and the next step is to convert them into another node. So when we convert them into another node, we call this build function that will match a single element, and when we have a single element in the list of nodes, we are able to stop the processing and return a Merkle tree with the proper root. So eventually the final new function will look something like this. It's taking a list of blocks, it's applying the hash function into each block, it's mapping each block into a leaf, and it's calling recursively the build function. So if we take the same example, if we take the same input and call the Merkle tree .new function, this time we'll have this kind of output. So we have a Merkle tree with a root, which is nothing more than a node that contains an hash that was the result of the computation of applying the one-way hash function to both child hashes, and it has a left leaf and it has a right leaf as well. So now we know how to compute a Merkle root and build a Merkle tree. One nice property of Merkle trees is that we can use them to verify that a specific piece of data belongs to a larger data set. And this Merkle audit proof is the missing nodes required to compute all of the nodes between the data blocks and the Merkle root. So if we calculate this, or if you compute this audit proof and it fails to produce the same root hash, it means that our data block is not present in the tree. So let's take for this example. We need to provide the proof that L1 exists in our tree. So we know how to, if we know the hash function, we know how to calculate the hash of L1. And in order to calculate the P1, we need only the hash of L2. With these 2 nodes, we know how to calculate P1, and when we know how to calculate P1, we need P2 to calculate the Merkle root. So I hope that the use of the tree authentication is now fairly clear. So when we compute the Merkle root, a given user A, it's responsible for transmitting this root to another user B, and A then transmits, the user A transmits the authentication path for L1. In this case, it's a list of nodes required, the additional list of nodes required to compute the Merkle root, which is H2 and P2. And since B already knows the root, it can authenticate itself the L1 data block. So we know that Merkle trees are especially useful in distributed peer-to-peer systems where same data should exist in multiple places and should be consistent. And by using Merkle trees, we can detect these inconsistencies between replicas. We can even reduce the amount of transferred data, and these enable peer-to-peer file sharing. And we can even maintain several versions of the same tree. So if we have a data file represented by a data structure, we are able to detect these inconsistencies between replicas of the same tree. Take, for example, these 3 replicas. They should be consistent. And at a given point in time, a repair coordinator will ask each replica the current state. So instead of sending all of its data, each replica will compute a Merkle root. And at a given point in time, the repair coordinator will receive these Merkle roots, and it's able, by just comparing the root nodes, it can make the repair coordinator can make sure that those replicas are inconsistent. So because the Merkle root is not the same. So in this case, replica 1 and replica 2 have the correct Merkle root, which is A. If you notice, replica 3 contains a data block L3 that is different than L2. So to compare the states of the 2 nodes, each replica will exchange the corresponding Merkle trees by levels, and they will only descend further down if the leaves or nodes are different. And if the 2 corresponding leaf nodes have different hashes, then it means that there are objects that are inconsistent and must be repaired. So the next step is replica 2 must replicate the data block L2 to the replica 3, and this will lead that replica 3 will need to calculate the Merkle root once again. And once the Merkle root is calculated, the repair process is completed, and now the 3 replicas have the same consistent state. So this is called anti-entropy mechanism, and databases like Dynamo, React, and Cassandra use this mechanism to repair their bad replicas. Another good use case of Merkle trees is peer-to-peer file sharing. We know that one of the advantages of Merkle trees is that each branch of the tree can be checked independently without requiring nodes to download the entire dataset. We saw this already when we were talking about audit proof. So let's take, for example, we are downloading a file from a torrent file from the internet, and we fetch the root from a trusted source to access a given file. So that Merkle root represents our file that we are interested in, and the peer that sent us this root, we trust them. The next step is to fetch the chunks of data from untrusted sources. So at least we know for sure that the root is legit, so we are able to fetch the rest of the tree from untrusted sources. And as we see in the audit proof, we know how to calculate the hash of L3, and we need to ask for the authentication path for L3. So that untrusted peer will send us the authentication path. We know how to calculate that node, so there's no need to transmit that. And once we have the authentication path completed, we know how to compute the root once again. And if the root computed from the audit path matches the true root from the tree, then it means that the audit path is a proof that the data block exists in the tree. And if the data block exists in the tree and the root is valid, it means that L3 is a legit data block. So another cool example of a cool usage of Merkle trees is copy on write. And copy on write data structures are also called persistent data structures, since the old version is always preserved. So we keep adding stuff to the data structure. We keep updating fields, for example, and the data structure is immutable, and it's creating always a new version. But with the copy on write, the old version is always preserved. So take this for example. This tree is already computed, but we are updating the data block L4. Since it is immutable, we need to calculate the hashes up to the root. But if you look at the left, both the data blocks and the hashes are still the same. So the idea of copy on write is, instead of taking a full copy, we can share the same tree between both copy and the original tree. And eventually it'll look something like this. So we can see that we are only adding a new data block, L4, and we are adding 3 new nodes. So we are computing 3 new hashes. All the other nodes and data blocks, and these data blocks could represent gigabytes of data, these nodes and the data blocks are being shared between both versions. So we are reducing space here. So eventually it'll look something like this. We have the version 1 and the version 2 with the added data block, the new computed 3 nodes, and all of the rest of the tree is being shared by both versions. So just to wrap up, just to highlight a few points of Merkle trees. So Merkle trees are just binary trees containing an infinite number of cryptographic hashes. Leaves. The leaves contains hashes of data blocks. The nodes contains hashes of their children, and they produce a root hash that is able to summarize an entire data set, and the root hash is publicly distributed across the network. And with Merkle trees, we can easily prove that a given data block exists in the tree. So if you are interested in diving even more into Merkle trees, you can find them in Cassandra, IPFS, React, Ethereum, Bitcoin, OpenZFS, and much more. And if you are a reading person like me, you have lots of papers to choose from. I would recommend you to read the Ralph Merkle papers, where they are the original papers that introduce Merkle trees. And I have this this talk I published today a blog post, and it contains several references to the papers and some blog posts from Cassandra and React. So feel free to go for it. And that's it for me. I want to thank you for listening to me, and have a nice conference. Thank you.
Hey, thanks for the talk. I'd like to know if there are any, like the library you've shown, is it open sourced, or is it like Elixir implementation of Merkle trees? And if yes, I would like to know if you can easily add things to the data set, because on the examples from the slide, you've always passed the entire data chunked. And what I would be more interested in is, if I have data that grows and I need to synchronize it between services, can I easily add them to the Merkle tree and then use those Merkle trees to make sure that both services have the same data?
So thank you for your question. The first question is if this is open source. It should be. I'm really ashamed to publicly distribute this code, but I will eventually pull this. I have this on my machine, so I will probably upload it to GitHub. The second question is, yes, I my examples were based on a data block. So the goal was to compute a Merkle root. But yes, you can have new nodes, new data blocks into a Merkle tree. They are quite not efficiently, but you can do it. You can do it. There's lots of cool implementation in Erlang, I think, that is using that way. So you are keep adding nodes and recalculating the Merkle roots. So yeah, you can do that. Thank you.